Now, limits where the output is getting really large are called infinite limits. We can also talk about limits where the input is getting very large. So we call those limits at infinity. Here's some examples. We just want to figure out, usually when we're taking a limit at infinity, what happens to this function in the long run as you go out on the graph a long way. So I've got some examples here. In this case, we have x getting really, really large. So we're going to have 1 over infinity cubed minus 3 times infinity squared minus 5 times infinity. Now, when you have infinity minus infinity, you have a large minus a large. That can be hard to say. So what we could do to figure out what this limit is to try to divide by the highest term in the denominator. What that will do essentially is make the denominator, instead of the denominator going all over the place, it will make the denominator settle down to some particular value. So when you see something like this, what you can do, limit at infinity, is to try to stop the denominator. So in this case, the denominator, the fastest growing term is x cubed, right? X cubed grows faster than x squared, which grows faster than x when x is large. So, okay, so we're going to divide top and bottom by that fastest growing term. Then we'll have in the top 1 over x cubed. Down below, if you take x cubed divided by x cubed, you have 1. If you have x squared divided by x cubed, that's 1 over x, so we have negative 3 over x. And negative 5x over x cubed would be negative 5 over x squared. Once we do that, it's a little clearer to see what's going to happen in this limit. As x gets larger and larger, the top, 1 divided by larger and larger numbers, is going to go to 0. And let's see, this 1 is going to stay fixed. Basically what we've done is to stop that fastest growing term because we divided by the fastest growing term. Now negative 3 over larger and larger numbers is going to go to 0. And as x gets larger and larger, x squared gets larger and larger. So negative 5 divided by larger and larger numbers is also going to go to 0. So we have for this limit 0 over 1, which is 0. So here's another example. In this case, as x goes to infinity, it may not be clear at first because we have like a large number x cubed, right? Minus 5 times infinity plus 4 over infinity cubed minus 3 times infinity squared minus 5 times infinity. Just trying to think about infinity as indicating a very large value. Well, what we can do is, since it's not really clear, we've got large numbers divided by large numbers, and that's not super certain as to what that could be. What we could do is try to stop the denominator by dividing by the fastest growing term. So in this case, the fastest growing term of the denominator is still x cubed, so I'm going to divide top and bottom by x cubed. When I do that, skip over here, and we have the limit as x tends to infinity of, in the numerator we have x cubed divided by x cubed, which is 1. 5 over x cubed just leaves an x squared downstairs, so we have minus 5 over x squared, and then we have plus 4 over x cubed. And downstairs we have 1 minus 3 over x minus 5 over x squared. Now it's a little easier to see what's going to happen as x gets larger and larger. This 1 doesn't care. 5 divided by bigger and bigger numbers is going to go to 0. 4 divided by bigger and bigger numbers is going to get smaller and smaller. It's going to go to 0. The 1 downstairs doesn't care. 3 divided by bigger and bigger numbers will go to 0, and 5 divided by bigger and bigger numbers will go to 0. So in this case we get 1 over 1, which is 1. Alright, here's one last example. And this function here, we've got the limit as x tends to infinity. Again, we have the top growing and the bottom growing. In order to figure out what to do, what we could do is stop the denominator so that it will settle down a little bit and we'll be able to see what's happening. So to stop the denominator, I'm going to divide top and bottom by the fastest growing term. And what we get on top is x plus x squared over x cubed would be 1 over x plus 4 over x cubed. And downstairs we have 1 minus 3 over x minus 5 over x squared. Okay, and now what we can see is that as x tends to infinity, the bottom is going to settle down to 1, and the top, these terms will become more and more insignificant the larger x is, right? 1 divided by larger and larger numbers is tinier. So in the long run, this function behaves like x. It grows like x. If x goes to infinity, this limit is going to be infinity. But we can get some more information about this graph if we use long division. So we saw that the limit of this function as x tends to infinity is infinity. But we can tell a little bit more about how this function goes to infinity if we'll actually do the division problem. Remember, every fraction is really just a division problem. In fact, if you look at our symbol for divide, it is a tiny fraction with one number on top and one number on the bottom. So this fraction means x to the fourth plus x squared plus 4 divided by x cubed minus 3x squared minus 5x. So in order to do division, what we do is first we choose a number to multiply by, then we multiply, then we subtract, and then we keep working on what's left. So if we compare the highest degree terms here, we have an x cubed and an x to the fourth. If I want to eliminate the x to the fourth, I'm going to have to multiply by x. That way, when I do multiply, I get x to the fourth, and x times negative 3x squared would give me negative 3x cubed, and x times negative 5x would give me negative 5x squared. Once I've multiplied, then the next step is to subtract. X to the fourth minus x to the fourth is nothing. X squared minus, let's see, there's not a cubic term here. I'm just subtracting negative 3x cubed, so I get 3x cubed. I have the x squared minus 5x squared, though, and that's going to give me 6x squared. And then finally I have 4 minus nothing. Now to figure out the next term, what I do is I say, well, what times x cubed would give 3x cubed? And the answer is 3. So 3 times x cubed would be 3x cubed. 3 times negative 3x squared would be negative 9x squared. And 3 times negative 5x would be negative 15x. So now that I've multiplied, let me subtract again. 3x cubed minus 3x cubed would be nothing. 6x squared minus 9x squared would be 6x squared plus 9x squared, or 15x squared. And then we have nothing minus 15x, so that would be plus 15x. And then finally 4. So what I have here, this is my remainder. When you're dividing, you always have your quotient plus remainder over divisor. So here's the remainder. Okay, so what we've done basically is taken our function and written it in a different way. We've written it as this linear polynomial x plus 3 plus this rational function, which came from the remainder divided by the divisor. Okay, so now we can see that this top part, or this remainder over divisor part, is going to disappear as x tends to infinity, because the limit as x tends to infinity of 15x squared plus 5x plus 4, if we stop the denominator by dividing by the fastest growing term in the denominator, which is x cubed, then we get the limit as x tends to infinity of, let's see, 15x squared divided by x cubed would be 15 over x plus 5 over x squared plus 4 over x cubed. And down below, x cubed divided by x cubed would be 1 minus 3 over x minus 5 over x cubed. And what's happening on the top is each of these terms is going to 0. So the top is getting very, very small. And the bottom, these terms fade away, but there's this 1 down here. So the limit in this case is 0. So what we found is if we have a rational function like this, a ratio of two polynomials, if the degree of the top is higher than the degree of the bottom, we can go ahead and do the division problem, and we get a polynomial plus a part that fades away as x tends to infinity. It actually fades away whether x goes to plus or minus infinity. So that means when we look at this function, in the long run, when x is really large, this term will be insignificant, and we'll have basically the function approaching this line x plus 3 as x goes to infinity. Let's just look at that. So pull up my graphing utility, and we'll just put this polynomial in here, x to the fourth plus x squared plus 4 divided by x cubed minus 3x squared minus 5x. We've got our graph. We figured out that in the long run this function should settle down to looking pretty much like x plus 3. So I plot that. Okay. Notice as we zoom out, there's our function. You can see until x gets about 10 away from the origin, there's lots of wiggling going on. That's determined by this remainder part, remainder over divisor. So that's a complicated function. But the further we get out, the more the function settles down to this line x plus 3. And we were able to analyze that by doing long division. We call this line x plus 3 a slant asymptote or an oblique asymptote. So we have this oblique asymptote that the graph is approaching. Remember, an asymptote is a line that the graph approaches, and so that fits the bill there. So if you hear slant asymptote or oblique asymptote, that's how you find one. You use long division.